In this video, you will learn what is ionization energy, how to represent ionization energies of an element in the form of an equation, factors affecting ionization energy, and trends in ionization energy in the periodic table. You'll also learn about what is electronegativity, factors affecting electronegativity, and trends in the electronegativity in the periodic table. Ionization energy, it is the energy required to remove 1 mole of the most loosely bound electron from an isolated gaseous atom or ion to produce 1 mole of gaseous cation, that is positively charged ion. It is typically measured in units of kilojoules per mole. So why do we want to measure ionization energy? Chemists use ionization energy as evidence to establish the concept of energy levels in atoms. It is used to tell us how stable is the atom and to deduce how likely is an atom to lose electrons to form cations, that is, predict reactivity and properties of molecules. So, when writing the equation for ionization energies, if the element is in a molecular state or liquid or solid state, it is important to first change it to its gaseous atomic state. Ionization energy is only measured when the element is in its gaseous atomic state. For example, N2 represents nitrogen in its gaseous molecular state. The molecule must be converted into its gaseous atomic state before measuring the ionization energy of nitrogen. And say if you have potassium, it normally exists in its solid state, and it is important to first convert it into its gaseous atomic state before ionization energy is measured. The first ionization energy is the energy required to remove 1 electron from the outermost energy level of the atom of an element. A cation with 1 positive charge is formed. The electron moves out of the influence of the nucleus of the atom. So, for example, the first ionization energy of nitrogen is 1251, and nitrogen with 1 positive charge in its gaseous state is formed. Nitrogen has 7 electrons, so each electron is removed one by one, and these are called successive ionization energies, and there is a literature value for each one of them. Now let us look at factors affecting ionization energies. The main factor is atomic radius. Larger atomic radius have electrons that are further away from the nucleus, reducing the force of attraction between the nucleus and the outermost electron. Therefore, less energy is required to remove an electron, and ionization energy is lower. In other words, larger the atomic radius, lower the ionization energy. Nuclear charge. With more number of protons in the nucleus, the nuclear charge is stronger, which makes its attraction towards the outermost electron stronger. Now this makes it harder to remove the electron, and therefore ionization energy is higher. In other words, more the number of protons in the nucleus, higher is the ionization energy. The inner electrons screen the nuclear attraction for the outermost electrons in the valence shell. Therefore, larger number of inner electrons decrease the ionization energy. So, for example, if you compare the ionization energies of sodium and magnesium, and here's the electron configuration, you'll see that sodium and magnesium both have the same number of energy levels, that is 3 each. They both have 10 inner electrons. That is the 1s2, 2s2, and 2p6. And sodium has 11 protons and magnesium has 12 protons. Now this makes a difference. Magnesium has greater nuclear charge, therefore smaller atomic radius. And if you look at the ionization energy, magnesium has a greater ionization energy than sodium. So the nuclear charge is the main factor that affects the ionization energy. However, if you compare the ionization energies of sodium and potassium, you'll see that sodium has 3 energy levels, while potassium has 4 energy levels. Sodium has 10 inner electrons. Potassium has 18 inner electrons. Sodium has 11 protons, while potassium has 19 protons. So it has greater nuclear charge, but because it has 4 energy levels, its ionization energy is lesser than that of sodium because its atomic radius is much larger. Now, if you look at the trend in ionization energy in the periodic table, the ionization energy increases across the period from left to right as the atomic size decreases, and ionization energy decreases down a group as the atomic size increases. This graph shows the first ionization energy of the first 20 elements. The ionization energy increases from lithium to neon in period 2 and sodium to argon in period 3. But you'll also see that there are exceptions to the increasing trends. That is, the ionization energy of beryllium is higher than that of boron, and nitrogen is higher than that of oxygen. Now this is because the electron is removed from the 2s2 orbital in beryllium and 2p3 orbital in nitrogen. These are more stable, fully filled and half-filled orbitals, and therefore their electron configuration is more stable and more energy is required to remove them. Similarly, magnesium has higher ionization energy than aluminum, and phosphorus has higher ionization energy than sulfur. And this is also because they have a more stable electron configuration than aluminum and sulfur. Let us now understand what is electronegativity. Recall that a chemical bond is formed between two atoms where electrons in the valence shell are either shared or transferred between them. So electronegativity is a relative measure of the tendency of an atom's ability to pull the electron density towards itself and away from any atom it bonds to. It is the relative power of an atom in a molecule to attract electrons towards itself. Note that electronegativity has no units. Measure of electronegativity is especially significant in covalent bonds, where electrons are shared between bonding atoms. The sharing is generally not equal. The more electronegative element pulls the shared pair of electrons towards itself. So, for example, in a molecule like chlorine, that is Cl2, the sharing is equal because the bonding atoms are of the same elements. However, in hydrochloric acid, chlorine pulls the shared pair of electrons towards itself because it is more electronegative than hydrogen, and this is shown by an arrow, and the sharing is unequal. We will later discuss the applications of electronegativity in structure and polarity of covalent molecules, as well as its role in understanding intermolecular forces of attraction between molecules. Now let us understand the factors affecting electronegativity. The first is the atomic radius. Larger atoms have lower electronegativity, and this is because the nucleus is further away from the bonding electrons, therefore it has less power to attract them. Then we have the nuclear charge. Atoms with higher number of protons or stronger nuclear charge have a stronger pull on the bonding electrons and therefore have higher electronegativity. And then there is screening effect. More screening effect reduces the nuclear attraction towards the shared electrons, so electronegativity decreases. In the periodic table, if you see the trends from left to right and top to bottom, electronegativity increases across a period from left to right as the atomic radius decreases, and electronegativity decreases down a group as the atomic radius increases. Fluorine has the highest electronegativity amongst all elements. So in the workbook, you'll get to practice questions on ionization energy and electronegativity and consolidate your understanding. So good luck and enjoy.